I'm going to talk about my project, which was about modeling of dust emission from crusted surfaces.
Yeah, just push the down button.
Okay. So let's just start with the importance of quantifying dust emission rate. So when we're talking about dust emission rate, we are talking about the vertical dust flux at the surface. So here in this picture, you can see the dust cycle in the Earth's system, and our work is focused on the dust emission part. So dust emission is a key component of the dust cycle, since when dust particles are usually rich in nutrition and organic matters, and then when they are transported by the turbulence, so they're going to be spread by the turbulence to the atmosphere, and they're going to be transported over the large distances, and they're going to provide nutrition for other ecosystems. On the other hand, for example, agricultural area maybe experience the coarsening of topsoil due to the lack of the nutrition. So dust emission is impacting human health and ecosystems. So it's important to work on the qualifying dust emission rate, so we cannot get the accurate estimation of the aerosol concentration in the atmosphere without getting an accurate estimation of dust emission rate. So what motivated us to work on dust emission modeling in southwestern United States? So dust storms are frequent phenomena in our areas, as Dr. Dubois mentioned in his presentation. So we are experiencing, a lot of crashes in southern part of New Mexico due to the low visibility of the roads. So it's a common phenomenon in our area, and it has been a common phenomenon in other areas too, like in Africa, Australia. So it's not a new problem. This is why several dust emission schemes have been developed during the past decades to estimate dust emission rates from different surfaces. So all these different dust emission schemes have their own assumptions for characterizing the surfaces. So this is why they are different in representing magnitude and frequency and particle size distribution in their models. But the problem is that our area is partly crusted, and most of these developed dust emission schemes have been tested against different data sets that are mostly sandy soils, and they haven't well tested against crusted surfaces. So this is why we decided to work on our area. So based on different systems, we have different definitions for particle sizes. But based on Shao 2008, we're going to consider particles with diameter less than 63 micrometer, which are mostly clay and silt particles, as dust. And the dust particles and the particles with diameter between 63 to 2,000 micrometer are sand. And different particles with different sizes, they're gonna get different modes of particle motions. For example, really small particles, they're gonna experience long-term suspension, which means that they're gonna stay in the atmosphere for maybe several days, and they're going to be transported over the large distances. But the particles with diameter between 20 to 70 micrometer maybe experience just short-term suspension, just like several hours. And then the larger particles, they're going to have saltation, but the real large particles with diameter larger than 500 micrometer, they are too heavy to be lifted by the wind, so they're gonna push through the surface by maybe saltating or wind. Okay, so we have three main dust emission mechanisms that are responsible for occurrence and magnitude of dust emission from different surfaces. The first one is aerodynamic entrainment. It means that the dust particles are lifted from the surface directly by the wind. Saltation bombardment, it means that when the dust particles, that they can be like the aggregates or any kind of grains strip the surface, they have some localized impact on the surface, which is strong enough to overcome the binding forces of the dust particles and create dust. And then we have aggregate disintegrations. In the natural conditions, some particles exist as like aggregates. So during the strong wind erosion processes, we're gonna see the fragmentation of the aggregates because of the wind or saltating particles. So the goal of this project was improving the representation of the magnitude, frequency, and particle size distribution of dust emission from crusted surfaces. So we test the applicability of one of these dust emission schemes named Shao 2004 to see how PM10 dust emission is estimated from crusted surfaces in New Mexico, USA. We just examined the capability of this scheme for 3 dust emission events in spring 2016. Our hypothesis is that the dust emission magnitude, frequency, and particle size characteristics for the crusted surfaces can be accurately estimated by this scheme by representing the soil particle size distribution that can reflect the characteristics of the surface crust and loose erodible material. So the objectives are evaluating the capacity of the scheme in predicting the magnitude and temporal evolution of the dust emission for crusted surfaces, and also detect and address the potential deficiencies of this scheme to enable dust emission modeling for crusted surfaces. So let's have a quick review on the studies that have done over the crust surfaces. So some of these studies are working on the impact of soil properties on dust emission. For example, Glit and then Nicklin had some studies on the impact of surface crust and soil properties on dust emission modeling. Or Rice et al. Did a series of studies on wind erosion rate based on the breakage resistance of crust to kinetic energy of saltating particles. But I want to focus more on the different dust emission schemes, because looking at different dust emission schemes help us to choose an appropriate dust emissions for predicting dust emission from the crusted surface, and also we can see the differences and see their specification and how appropriate they are to estimate dust emission for crusted surfaces. So as you can see from this table, so some of these schemes are empirical, some of them are physics-based, and also we can categorize them based on 2 types. Like we can categorize them into 2 types, like some of them are energy-based and some of them are volume removal-based. The energy-based dust emission schemes are estimating dust emission based on the binding forces of the particles and the kinetic energy of the saltating particles. And the volume removal-based dust emission schemes are estimating the volume of the eroded material due to the impact of saltating particles. So if we go through different schemes, you can see, for example, the Gidel and Passy's empirical energy-based dust emission scheme, and saltation bombardment is the main mechanism for creating dust emission from different surfaces. But this mechanism is different for different dust emission schemes. For example, for Close et al., the main mechanism is aerodynamic entrainment. But looking at different dust emission schemes help us to choose Shao 2004 for our work to examine against crusted surfaces because of 3 reasons. One of them is that Shao 2004 scheme is a size resolve scheme, so it means that we can get dust emission for different particle sizes. And also, it has considered 2 main mechanisms of dust emission, which are saltation, bombardment, and aggregate disintegration. Fragmentation of the aggregates has been considered as the main mechanism of creating dust from the crusted surfaces. And also, so this scheme also give us an opportunity to enter minimally and fully particle size distribution for calculating the dust emission rate. So, you can see that table. Okay, so in that table, I was explaining the structure of the dust emissions. So first, we're going to have some input for the scheme, and we're going to calculate threshold friction velocity based on that input. And then we're going to calculate saltation flux. And then based on these two, we're going to calculate the total dust emission. This equation shows the Shao's scheme. According to this equation, you can see, so we're going to cover both aggregate disintegration and saltation bombardment using this scheme. And then I'm going to go through three main parameters, which I'm going to modify through the experiments to get a better result for dust emission rate from crusted surfaces. These are three main parameters of Shao's scheme. First one is gamma, which is the function shows the. Oh, okay. Here the gamma is the function showing that how easily the aggregate dust are gonna release, and then we're gonna change the degree of the aggregate disintegration by changing kappa. And then we have sigma p shows the ratio between the fraction of the dust and aggregate and that of the aggregated dust, or maybe it can be translated to the fraction of minimally dispersed particle size distribution to fully dispersed particle size distribution. And then we have bombardment efficiency, which is going to be changed based on the plastic pressure. And the plastic pressure shows the hardness of the surface. And we have defined our experimental area based on these parameters and also the changing particle size distribution. So our study area was located in the Jornada experimental range in southern New Mexico, and we just worked in 3 events, 23rd of March 2016 and 2 events in April 2016. Here in this picture, you can see how the instruments were deployed in the area. So we had some meteorological instruments and some sediment flux measurements instruments. We had some instruments to measure the vertical and horizontal flux. So in general, we can say that we were collecting 4 different categories of observational data. First, we focused on land surface properties, which are data related to the total land cover and vegetation cover using the LPI method. And then we were collecting atmospheric properties using the meteorological, using the Med tower, and then we were collecting horizontal and vertical sediment flux data using dust tracks and sand trees. And then we collected soil samples, 3 different soil samples. First, the parent soil, which was the 1 centimeter of topsoil, and then loose erodible material and crust samples. In this picture, these are some pictures of our area showing that it has mostly covered with the loose erodible material and partly crusted, but the crust surface, the crust layer is really thin and it's really easy to break. And then we have spare vegetation cover. And here in this pie chart, we can see the fraction of the loose erodible material and crusted soil. As you can see from this pie chart, the most area is covered by loose erodible material, and we have just only like 20% of crusted soil. The way that we are presenting particle size distribution in our model is using a sum of 4 log normal distribution. So we are feeding the observed data using means of nonlinear least square method to find out the fitting parameter that we can use in our model to present particle size distribution. I have shown one example of these particle size distribution in this graph. As you can see that the observed data and the models are really overlap, showing that the data have been fitted to the model really well, and there isn't a big difference between the dry and wet particle size distribution for the parent soil. Okay, let's go through the numerical experiment settings. So we had 3 experiments. First, we ran Shao's scheme by default setting, and then we used the minimally and fully dispersed particle size distribution of the parent soil. And then for the second experiment, we tried to rescale the saltation flux and modify some of the scheme parameters to get a better result, to get a better magnitude and timing of the dust emission, and then dust emission flux. And then for the second experiment, we tried to have a better representation of particle size distribution by replacing minimally and fully particle size distribution with the LEM and crust PSDs. So the results showed that when we were running dust emission just using the default setting and using the parent soil minimally and fully dispersed particle size distribution, the dust emission flux was significantly overestimated for all events. So when I'm talking about the default settings, means that Shao's scheme have been tested against different data sets, so they have came up with the range of the values for different parameters in their studies. So I use those data for running the model. Since we're calculating the dust emission flux based on the saltation flux, we compared the observed saltation with the model saltation using White 1970 scheme, and we found that the saltation was overestimated by 3 orders of magnitude using the White scheme. So it wasn't unexpected because we don't have unlimited saltating particles now on the surface, and it's a little bit crusted. So the model was overestimated. This is why we try to scale saltation flux and then use the scaled saltation flux for running Shao's scheme for the second experiment. In the second experiment, we used parent soil minimally and fully particle size distribution while we have a scale saltation flux, and we try to modify scheme parameters to get a better results, get a better timing and magnitude of dust emission flux. So here in these 2 graphs, I have compared the second and third experiments. So for this experiment, we just replace the scale saltation flux and we work on the scheme parameters. But for the second experiment, we try to have a better representation of the particle size distribution, because we found that we are not covering the variation of the magnitudes of saltation of the dust emission flux. So this is so in the experiment 2, for dust in the experiment 2, as we can see from the graphs, so we were getting the better magnitude and timing by having a better representation of the particle size distribution by replacing the fully dispersed PSDs with the crust PSD and minimally dispersed PSD with the LEM PSDs. So it means that we are going to improve the representation of PSDs by replacing crust and LEM PSD in the model. So here you can see how the results can be improved by having a better representation of the soil characteristics in the model for one event. And then I'm going to show you another example for 25th April 2016. As you can see, for the experiment one, we just rescaling the saltation flux and adapting appropriate scheme parameters, we could get somehow good magnitude and timing of the dust flux. But by having a better representation of the PSDs, we could get much better timing and a magnitude of dust flux. So as discussion, I just want to go through some uncertainties of our research. For sure, there are some uncertainties on particle size distribution analysis because different studies are using different instruments for measuring PSDs, and there are different particles, and somehow for fully dispersed particle size distribution, in some studies they have used chemical and some they are using just water, so the results could be different. And there are some errors in sampling design, data collections. Also, we just collected data for 3 events. For sure, collecting more data help us to generalize our results. And then there have been some limitation on measuring saltation flux. We just had data about we had data for just 2 events. More data on saltation flux will help us to compare our data, our estimated saltation flux with the measurements, so we're going to validate our model better. And then there are some limitations which shows the scheme based on its assumptions, and also we know that the surface is like spatially and temporally changing, so these dynamic heterogeneous surfaces are not covered with the model. So as a conclusion, we can conclude that by adapting, by modifying the scheme parameters, we could get the better magnitude of timing saltation flux. But by having a better representation of particle size distribution, by having a better representation of soil characteristics, we could improve the magnitude, timing, and we could improve the representation of timing, magnitude, and particle size distribution in the model. But further tests are required in future to investigate the parameter variability for different crusted surfaces. And then by having more data, more examinations, we can generalize our data and our results to other surfaces too. So, thank you.
All right, so thank you. Thank you, Vida. Let me, we'll transition out Vida's presentation. I think we're pretty